In the last episode, we saw the three phases of transmission. Now we ask a dangerous question. What do we call congestion? Packets tell the secrets, Wireshark listens, and you see the truth. I'm Tai Feng, and welcome back to my network analysis class. What actually defines congestion? The answer isn't as simple as you might think, and how you answer it determines the type of congestion control algorithm you'll create. Let's consider three options. Option A. Congestion begins when the sending rate approaches the bottleneck bandwidth. At this point, the amount of data in flight approaches the BDP, bandwidth delay product. This is the optimal operating point we introduced in the previous episode. Here the pipe is fully utilized, but queues have not started building yet. Option B, congestion begins when queues start forming. Packets are not lost yet, but RTT begins to increase. This means the path is already carrying more data than the pipe can immediately deliver, so packets start waiting in buffers. This is the bandwidth-limited phase. Option C, congestion begins when buffers overflow and packets are dropped. This is the buffer-limited phase. In fact, different congestion control algorithms choose different answers. The definition of congestion isn't universal, it's a matter of philosophy. How you define the start of congestion dictates how you will try to control it. Loss-based algorithms treat any packet loss as the signal of congestion. This corresponds to option C, operating in the buffer-limited phase. This philosophy shaped the classic TCP congestion control design for decades. Delay-based algorithms use increases in RTT as its cue for congestion. This corresponds to the choice of option B. The Vegas algorithm is a typical representative. Hybrid algorithms combine loss and delay signals, or even try to determine the cause of loss. For example, compound TCP, Westwood. They try to balance throughput and latency. Model-based algorithms, for example, BBR, tries to build a model of the path to find the optimum operating point. The goal it pursues is the optimum operating point mentioned in option A. The goal is simple: keep the pipe full, but avoid building queues. These algorithms are all doing congestion control, but in wildly different ways. So, what is true congestion? Different congestion control algorithms define congestion differently, shaped by their design philosophy and by the network conditions of the internet at the time they were created. But from the perspective of network dynamics, the situation is clearer. Realistically, congestion starts as soon as queuing begins and RTT starts to rise. So from the moment RTT climbs above the base RTT, you're experiencing congestion. In other words, once queues begin to build, the network is already in a congestion state. This understanding is not only more faithful to reality, but it is also the foundational concept behind BBR. It helps us better understand network conditions and performance. In dedicated lessons, I'll dive into the details of how these algorithms work and how BBR hunts for that perfect operating point. Hit subscribe if you don't want to miss it. All right, let's quickly recap. Different algorithms choose different signals. Loss-based, delay-based, hybrid, and model-based approaches. But from a network dynamics perspective, congestion effectively starts the moment queues begin to form and RTT begins to rise. That's all for today. Until now, everything lives in theory about the network congestion model. But how do we see this in real packet captures? In the next episode, we open Wireshark and make the packets confess.